It's really a pleasure to attend this event. As I said earlier, I can't believe Mike is already 60. For me, he is this young, promising postdoc whom I met at Rutgers 5 years ago. I'd like to thank everybody for the invitation, for inviting me to speak at this wonderful event. And as I give talks in such birthdays, I always try to look at my old photos and see if I can find a photo with the birthday boy. And the best I could come up with is these two photos. And I leave it as a puzzle for you to identify all the people. We see a lot of good friends here. Some of them are in the audience here. And the main lesson from that, so here is Mike, and here is Mike a few years later. Is I think the main lesson from that is we have aged a bit between these two photos. I think Michael Green, John Schwartz and others are there in the audience. So I think this must have been John Schwartz's birthday, if I'm not mistaken. In any event, Mike and I have co-authored 5 papers. These are the papers. And the collaboration on these papers has been a lot of fun, and they were completely different. This paper is particularly special because the work on this paper, probing F-theory with brain, took a whole hour. From the first conversation on the topic until everything was clear was less than an hour, if I remember correctly, and maybe Mike can correct me. I think this is still my record for a paper. It was not a bad paper. Other papers here took longer than 1 hour. Some of them took much longer. But unfortunately, the fact that there are only 5 papers does not give a clear description or an honest description of our interactions, because over the years, we have had many, many conversations about many topics, Mike's research, my own research, other people's work, and I've learned a lot from Mike. He has this fantastic way of getting to the bottom of the matter very rapidly. If I have to summarize Michael in one word, the word I would pick would be brilliance. I'm sure that everyone here would agree that every sentence that Mike says is non-trivial and extremely deep. And although on occasions I don't fully understand what he says, I've learned over the years that it's worth the effort to try and really get to the bottom of it, because whenever he says something, it's worth understanding. So after this introduction, I'd like to present my work here, and hopefully Mike will appreciate it, enjoy it, and maybe he will offer some of his insights so that we can push the research forward. So this is the longer title. The short title is Exotic Field Theories, but this is something I've been doing over the last 2 or 3 years, 2.5 years, putting together distinct ideas. Most of them are common in condensed matter physics, not in high energy physics. But I'll pitch this talk mostly to a high energy theory audience rather than to condensed matter people. And these are my collaborators. This is the reference to a recent paper. We have written a long list of papers which have more references in them. But I thought I would share with you a picture of the collaboration. This is really a typical way how we collaborated. And I thank them not only for the collaboration, but also for helping my mental state during this painful period. So let me go to the subject itself. There are a number of exotic lattice theories. Usually they are not lumped together, but I would like to lump them together here. An example is something called the XY plaquette model. Is a model on the lattice, originally by Paramacenti, Balance, Fisher, with a lot of follow-up. There are various models of fractons. I'll discuss some of them soon, starting with the work of Shamon and then Ha, Vijay Ha and Dipole, and then a whole flood of papers. And the one aspect of them, and there are many other models I'll discuss today, the Lifshitz model, for example. And the common feature that I find exciting in all of them is that they do not have a standard continuum limit. And this is something that should bother every continuum field theory, is that there are lattice models with local interactions. They look totally innocent, but they don't have a standard continuum limit. So as I said, they are defined on the standard lattice. Everything looks completely conventional. They're short-range interactions, but the low-energy behavior is not captured by a continuum quantum field theory. And therefore, the existence of these models is a clear counterexample to the dogma that whatever you do at short distances, at long distances, you can summarize it by a local field theory. And you can trace this challenge, why it is so difficult to find a continuum field theory, to their peculiar properties. So there are a number of things. I'm just doing phenomenology here, scanning the literature and looking at models. So one aspect of these models is that they have either exact or emergent unusual global symmetries. These are global symmetries that depend on position. So if we have spins, we don't rotate the spins over the whole lattice, but only on the subspace of the lattice, and it is still a global symmetry. The second peculiar feature, which seems unrelated to the first one, is that they have excitations with restricted mobility. These are particles that are restricted to a point, or they can move along a line but cannot get out of the line, or on more complicated shapes. I want to emphasize that the restricted mobility is not just a question of energetics, that if I only pump more energy into the system, the particle can move away from the point. But instead, it's something a lot more fundamental than that. The particle cannot move, period. That's the end. It's not a question of energetics. The third, seemingly unrelated point is the large ground state degeneracy. So you formulate the system on a finite lattice, say with periodic boundary conditions with Lx, Ly, and Lz lattice sites in the different directions. And the typical formula for the ground state degeneracy is some number, say 2, to a function of the length. So you can think of this function k as being the log of the number of ground states or the entropy. And it's a crazy function of the Li's, of the different directions. The limit Li goes to infinity is not well defined, and it's often infinite. That by itself should tell you that there shouldn't be a standard field theory to it, because in field theory, the number of ground states is always finite. It could be 1, so there would be only one state, or there could be some finite number, but it does not go to infinity as L goes to infinity. And even more so, as we take L to infinity, there should be a well-defined limit. So that's not true here. Somewhat related to this thing is a phenomenon I like to call UVIR mixing. Long distance, we've seen UVIR mixing happening in examples originating from string theory, say the little string theory, non-commutative geometry that Mike worked on. And of course, any theory of gravity exhibits UVIR mixing. The other two examples are examples without gravity. What happens here is that this phenomenon happens in a lattice model. So it's not that we don't, in the context of the examples from string theory, one could say, well, we don't fully understand it. Maybe there's something at short distances which explains it. But in these examples, there's nowhere to hide because we have an underlying lattice. Everything is well defined at short distances. And yet long distance phenomena are very sensitive to short distance details. The example here with the ground state degeneracy is an example of this. And there are, of course, many others. So the research program that we have embarked on is to understand these phenomena, to understand whether they are related to each other or not, and to see how we can think of these theories, how to organize them, and how to phrase them as much as possible in the language of continuum field theory, despite the obvious difficulties. So what kind of Lagrangians have people studied? So if you just take these lattice models and you follow your nose and go to long wavelength and expand in derivatives, you find very unusual Lagrangians. And schematically, I can write them as follows. So here is one example. So there's a standard derivative in time, but then the spatial derivatives, we have only two terms with 4 derivatives rather than terms with 2 derivatives. And a number of people studied such theories. There's huge literature on that. And the sum over I and j can be over all of them or a subset of them, etc. There are also similar gauge theories that people study. I'll say more about these examples soon. So this is electric field square minus magnetic field square. The gauge fields have, the time component has a standard gauge transformation laws, but the spatial component very strange. The spatial gauge field is a tensor, Aij, which transforms with a double derivative of alpha, the gauge parameter. And these are gauge invariant electric and magnetic fields. By the way, these theories with these funny gauge fields were originally introduced by Shu and later by Shu and Wu, kind of a variant of his example. And they were introduced as a way of getting gravity out of the lattice. So the idea was that the metric would be this gauge field with two symmetric indices. Personally, I think that this direction is totally misguided. However, these gauge theories still exist, and Pretko was the first to show how they are related to fractons, and I'll say more about that later. So, and again, the key point here is that we have more derivatives than usual, both here and here, and that propagates through the whole discussion. And once we have such gauge theories, we can also have BF Lagrangians. So we can write various BF Lagrangians, which are higher derivatives than the standard ones, but we can write them down. Now, the higher derivative terms lead to important subtleties. And one question we would like to address is, what does such a continuum field theory mean? So one starting point is to start from the lattice and say, I'm not interested in the continuum theory, I'm only interested in the lattice. So I'll just study the lattice theory and that's it. Another point of view is that I'm not interested in the lattice, I'm only interested in the continuum Lagrangian. Here is a Lagrangian that somebody wrote down. We should be able to understand what it means to have this Lagrangian. What does field theory based on such a Lagrangian mean? And specifically, when we have such Lagrangians, as we will see, we'll need to understand discontinuous field configurations. Normally, we don't have to think about them because the action suppresses them, but that's not the case here. And when we have gauge fields, there will be questions of the global structure. How are fluxes quantized? What are the gauge invariant operators and what are the allowed defects? So this is an important question that we will have to address. I actually think that focusing only on the continuum Lagrangian or focusing only on the lattice model gives you only a tiny aspect of the interesting topic. And a much more interesting question is, what is the relation between these continuum theories and the underlying lattice models? The underlying lattice model makes sense. We can take a limit perhaps and find the continuum theory. What kind of limit should we take so that we recover this continuum limit? Are there other continuum limits that we could take that would also be interesting? What do we mean when we write such a continuum theory? So there's huge literature on writing a continuum Lagrangian and how to regularize it and what it means, etc. These models show that it's a lot more subtle than we are familiar with. And the consequence of this understanding is how to organize all these theories, both on the lattice and on the continuum. We'd like to have some kind of a classification of them. So far, the examples that people found out were kind of discovered by accident. People did not look for, let's look for exotic models. They just stumbled on them and then say, oh, this model is very peculiar. I believe that there are many other examples. In fact, we are writing a paper now about other examples, but we would like to have some kind of an organization, some kind of a classification, which might lead to also more examples. So this is a short talk, and since this is a short talk, I decided I'll do what's normally done in high energy theory, is to focus on the absolute simplest example. The absolute simplest example and analyze it. And what I will sacrifice by that is that the simplest example will not be the most interesting one. This will be an example that demonstrates some of the phenomena, hopefully in the simplest possible way, at least as the simplest I'm aware of, but will not have the full richness of the more complicated examples. So I'll be talking mostly about 1 + 1 dimension, one space dimension, one time direction, and on the lattice and in the continuum. And we will see that some of the topics I mentioned earlier, particles of restricted mobility, funny ground state degeneracy, UVIR mixing, and so forth, can be demonstrated already there. But I emphasize that these models that I will discuss suffer from a lot of deficiencies. I'll mention them later. And these deficiencies are not present in their higher dimensional counterparts. So this was kind of more of a pedagogical way into the topic where we focus on the simplest example. So this was a long introduction. Let me go to the material. I'll be interested in this Lagrangian. It comes under the name of Lifshitz theory. And we can view this on, I'm going to start from the continuum here. And we can think of this Lagrangian either with phi being a real field, ranging from -infinity to +infinity, or we can say that phi is a compact field, so phi is identified with phi plus 2 pi. Is it natural? So the main point about this Lagrangian is that the two derivative term is missing. There's no two derivative terms. And the first question is it natural in the high energy theory sense? Maybe I should say in the 'T' sense. And the answer is yes, because it's protected by a symmetry. So what are the symmetries of this problem? We can shift phi by a constant. This is clearly a global symmetry. But we can also shift phi by a function linear in x. We shift phi by a constant times x, the action is invariant. And if we have a two derivative term, the action will not be invariant. So this symmetry justifies dropping the two derivative term. Let's discuss these global symmetries more carefully. First, the shift by C. Since phi is circle valued, C is circle valued. So this symmetry is a U1 symmetry, not R, but U1. And we can follow Netter procedure and write a conserved current. So there's a current with a time component and a space component, and it satisfies a funny conservation equation with two derivatives here. That just follows from Netter procedure, or if you wish, follows from the equation of motion from this Lagrangian. And then we have a conserved charge. We just take the time component of the current, we integrate it over space, and this is the charge that implements this transformation. So this part is easy. The reason this model is interesting is because of this other symmetry. We'll refer to it as a dipole symmetry for reasons which will soon be clear. The dipole charge, we can just follow our nose and say this is the charge. Notice that just as this Q is conserved, this object is also conserved, because if we hit it by d by dt, we can use the equation to write it as two derivatives of j, integrate by parts, and this charge appears to be conserved. However, and therefore we would say, okay, we have a dipole symmetry shifting phi by x. But this is way too fast, because this operator does not behave well at infinity. It grows as x goes to infinity. So if we are in non-compact space, we'll have to worry exactly what space of functions are we talking about? What are the boundary conditions as phi go to infinity? And if we have compact space with periodic boundary conditions, then this thing is not even well defined. So what are we talking about? So let's do it more carefully. This is the Lagrangian, this is the symmetry, and we need to understand what it means, what this dipole symmetry means. So we'll take phi to be a circle. So first of all, if we need space to be a circle or space to be compact to make sense of any of these subtle discussions. And then if phi is non-compact, this violates the boundary conditions, so the symmetry is not there. So the best we can hope for is to have the symmetry if space is a circle and phi is a circle. So phi is the map from a circle space to a circle, the target space. But now we see that this dipole symmetry is not U1, it's not R, but in fact it is Z. It's the group of integers, because we can shift phi by an integer times x, provided the integer is normalized properly. It's 2 pi over L. So this is the global symmetry. The global symmetry is not, this is an ordinary U1 symmetry, but this global symmetry is actually Z rather than a continuous symmetry. Now, we can also discuss winding configurations. So when we have a compact bosons, there is a momentum symmetry and a winding symmetry. And we can check that such a winding configuration is allowed because phi is circle valued, and it has zero energy for all integer m. What this means is that every state in the Hilbert space is infinitely degenerate. So this system is a bit sick. Every state in the Hilbert space is infinitely degenerate, and because we can always shift this configuration to phi. In an ordinary compact boson, such a configuration has energy proportional to m squared. In our case, this configuration has zero energy. One aspect of it that we immediately see is that this system exhibits UBIR mixing. We have zero energy states with arbitrarily large spatial derivative. Spatial derivative is proportional to m, if the slope of the function is linear, so the function is exactly linear, then we can make it arbitrarily steep and it still has zero energy. The system also has a winding symmetry. So anybody who is familiar with the compact boson immediately recognizes that this is a conserved current. It doesn't even depend what the action is. So this is a conserved current. And there is a winding charge when we integrate this current over all of space. So the configuration that I discussed earlier that winds around space carries winding charge. And the dipole symmetry shifts phi by a winding mode. What this means is that the dipole symmetry that shifts phi by such a configuration does not commute with the winding symmetry. So the symmetry of this problem is there's a U1 symmetry, that's the ordinary momentum that we know and love. There is a U1, which is the winding symmetry that we are also familiar with. And the Z momentum dipole symmetry that shifts phi by a term linear in X does not commute with the winding. And since this symmetry does not commute with winding, the Hilbert space has to realize this algebra where momentum and winding do not commute. And that's what underlies the degeneracy. This is the simplest representation of this algebra is infinite dimensional. So the reason we had this funny degeneracy, this infinite degeneracy, can be traced to lack of commutativity of these two symmetries. In fancier way, we could say that these two symmetries have an 't Hooft anomaly between them, and the 't Hooft anomaly is reflected in the large degeneracy. At this point, every person should feel very uneasy. It's true that we started with an innocent-looking Lagrangian, but we find a whole set of very strange, perhaps even singular behavior. Infinite degeneracy in the ground state, and so fields with arbitrarily large derivatives participating in the low energy theory. So we should ask ourselves, is this analysis sensible? Are the last several slides, do they really make sense or not? So the way to answer this question is to go back to the lattice. So we're going to regularize everything, put everything on the lattice, then it will manifestly make sense. And then we'll just have to take the continuum limit and see what we find. So I'm going to put the compact Lifshitz theory on the lattice. So here is my lattice. I've used Euclidean lattice. And there are spatial directions and time directions. Everything is discretized. For lack of time, I'm not going to give the details, but I would just say that there's a well-defined action with phi at the sides, some integer fields. This is a Villain type action on the links and the sides, and then some phi tildes on the plaquettes. The details don't matter. If you want, well, they do matter if you want to do something in practice, but for the sake of this discussion, just take my word that there is an action, it has some symmetries, and the functional integral is manifestly well defined. In fact, it's a Gaussian integral and Gaussian sums over the various fields, so the functional integral makes sense. It's a finite integral and a finite sum, so it makes sense. And there is a global symmetry. There's a U1 times ZL momentum symmetry. We call that L is the number of sites in the space direction. So we regularize space in its ZL. That's the momentum symmetry. And the winding symmetry is U1 times ZL. All these momentum and winding symmetries exist already on the lattice, including the 't Hooft anomaly between them, showing that this ZL does not commute with this ZL. And therefore, this lattice model has an L-fold degeneracy. So if the ground state, so every state in the system, if we think of it in the Hilbert space picture, has L, the degeneracy is L. So it's going to be infinite in the continuum limit. So now we take the continuum limit and we should just trace the symmetries. So the continuum limit is L goes to infinity. And in the continuum limit, this becomes a derivative in time. This becomes the derivatives in space. And we can trace what happened to the symmetries. We can track what happens to the symmetries. So the U1 momentum becomes remains U1. This is standard. As L goes to infinity, this ZL becomes Z. You can ask, what is the L going to infinity limit of the group ZL? And you can say that the limit is Z. And so the momentum symmetry and the dipole momentum symmetry that I mentioned earlier exist on the lattice. They're completely regularized. And in the limit, we find U1 times Z. This U1 symmetry is completely gone. It doesn't act on anything in the continuum limit. And this ZL, the winding symmetry, becomes U1 in the continuum limit. Now, already here we see something interesting. We can ask, if we have a group ZL, L is an integer. What is the limit of this group as L goes to infinity? There are many different answers to this question. One way of taking the limit, the group of ZL as L goes to infinity, is Z, because the number L gets bigger and bigger. Another way of thinking about it is that the group ZL are points on the circle, and as we take the L going to infinity limit, the points on the circle becomes denser and denser, and therefore the group becomes U1. One lesson from that is something that is actually quite standard in all these theories. There's a well-defined lattice action, and depending on how you take L to infinity, you get different answers. There's no unique answer as you take L to infinity. In fact, this action on the lattice is very interesting. It has exact self-duality and so forth, and it's of course completely meaningful. And it has many different continuum limits. So this was my brief summary of this theory of phi, this Lifshitz theory with a compact target space. And now I'd like to move to a gauge theory, because once we have a system with a global symmetry, we could ask what happens when we gauge it. And it's clear what needs to be done. This is a textbook thing, so we'll just follow our nose and follow the textbook discussion. So in the theory that we discussed, we had a conserved current satisfying such a conservation equation. D by dt of jt is the second derivative of x of j with respect to x. So Shu and Pretko, I also mentioned it earlier, said, what happens if we couple it to a gauge field? If we couple it to a gauge field, we should just write jt times at plus j times a. And then the gauge transformations are the changes in the gauge field such that using the conservation equation, the action remains invariant. So now we can throw away the matter theory and study just the gauge theory on its own. So we have some gauge theory with time component of the gauge field is this, the space component of the gauge field is this. We call it the tensor gauge theory because we're in one spatial dimension, so it's not a big deal to call it. It's funny to call it a tensor, but it makes sense to call it AXX because there are two X derivatives here. And in higher dimensions, this becomes AIJ, which is a symmetric tensor. So this is the gauge theory. This is the gauge principle. And I gotta say that the first time I said that, I told myself, there's no way this thing makes sense, because gauge theories have only one derivative. What are we talking about here? But this thing exists, so we ought to make sense of it. And that's what I'll do in the coming slides. So we have a gauge theory. We can form gauge invariant electric and magnetic fields. Since we are in 1+1 dimensions, there's no magnetic field, there's only an electric field. And you can check that this combination is gauge invariant. So if you wish, this is the curvature of this connection. Although this is not quite a connection because we have a double derivative here. And the Lagrangian is proportional to E squared. And just as I asked about the Lifshitz theory before, this is some continuum Lagrangian with some second derivatives. And we can ask, what does such a gauge theory mean? Is it sensible at all? What are the observables? Is flux quantized or not? Is there a return class or not? What is the analog of Wilson line? We should be able to answer all these questions. So what does it mean? And specifically, what are the global properties of this gauge theory? So it's again a textbook thing. We write these gauge transformations, and we said that phi was compact for circle value. So we impose that alpha is circle value. So alpha is identified with alpha plus 2 pi. And then we ask ourselves, what happens if we have such a gauge theory with alpha being circle value? What are the transition functions? What are the observables, etc.? And the simplest way to analyze that, remember our space-time is 1+1 dimensional. So we go to Euclidean space, we put the system on a torus. So Euclidean time is compactified and space is compactified. And now we study the effect of large gauge transformation. What are the large gauge transformations? They wind around the Euclidean time and they wind around the Euclidean space. So this should be an allowed gauge transformation with integers n tau and nx. And now we can study Wilson lines. And the Wilson's lines should be constrained such that they are invariant under this large gauge transformation. These are the rules, and we just try to follow the rules. Since our system is non-relativistic, we should treat tau and x differently. In fact, already in the gauge transformations, you see that time, this is with Lorentzian signature, the time we have first derivative, and in space we have two derivatives. So this is a non-relativistic system, and therefore we should be careful distinguishing defects in operators. This is something that in relativistic systems we rarely distinguish. We have Wilson lines that could be along the space directions or along the time directions, but here they're fundamentally different, so we should distinguish between them. So I try to use a color code. All the defects are in red, and all the operators are in this blue. So gauge transformation around that winds around time quantizes the coefficient here m in the defect. This is the same as in ordinary Wilson lines, in an ordinary U1 gauge theory. So as far as this object is concerned, we don't care how A transforms. And along the time direction, we have an ordinary gauge transformation, so it quantizes the charge. In the space direction, it's a little bit unusual because of the second derivative here, this object is gauge invariant on its own. We don't need to exponentiate it, let alone exponentiate it with an integer charge. So the defect is quantized, and the operator is not. The defect represents, as in ordinary U1 gauge theory, it represents the word line of a charged particle. So we have a particle with charge m, and it tries to move in time. So in this picture, it is at position x, and it runs along time. And then we can ask, can it move? In ordinary Maxwell theory, it can move because I can put ax dx and have a curve. In this case, we don't have ax, so gauge invariance forces this object to be at one point. Notice this is not a question of energetics. This is a statement that this operator, just by gauge invariant, this defect, just by gauge invariant, cannot move. The operator is also strange because it cannot we don't exponentiate it. In fact, if we follow the dimension of a tau is 1, so the dimension of this combination is 0, we can put it in the exponent. The dimension of this gauge invariant object is 1. Since it's dimension 1, it doesn't even make sense to put it in the exponent. I like to say everything we say in terms of global symmetries, because global symmetry is a way to organize things we don't understand. So I'd like to have a little digression and discuss something that is understood very well in a new language. So that would be a digression. And the digression would be into ordinary U1 gauge theory. An ordinary relativistic U1 gauge theory has a one-form global symmetry. So I use an index mu both for space and for time. And this is a symmetry that shifts a mu, again, we are on the torus, say, by a constant lambda mu over L mu. This is almost like a gauge transformation, but it's a gauge transformation that is not single value, does not satisfy the boundary conditions, and therefore it's not a gauge transformation. It leaves the action invariant, and therefore it's a global symmetry. So for the Euclidean torus, we have this global symmetry. Now our system, the system we're interested in, is non-relativistic. So let's phrase the one-form global symmetry in non-relativistic terms. So I'm going to state something that is well understood and phrase it in a non-relativistic language. It's very awkward for this system, for the relativistic system, but that's what we need in our other gauge theory, which is non-relativistic. So the spatial components here, lambda I, where I acts on space, they act as an ordinary global symmetry. They act on the states in the Hilbert space, and they act on the operators. So these are transformations that act at fixed time and transform one state to another, map one operator to another, operators transform by conjugation, etc. The temporal component, when we put tau here, if we are in Euclidean space, does not act on the Hilbert space. In fact, when we go to the Hilbert space, we choose a temporal gauge, AT equals 0 or A tau equals 0, and then we're not even allowed to make such a transformation. Instead, it acts on the defects. So the defect transforms under this global symmetry transformation by a phase. So we can say that the charge m of the Wilson line, when it is a defect, it is really the effect of the time-like global symmetry. When this Wilson line is space-like, the charge m is a result of is a result of the space component of the symmetry. So the space components affect the operators and the states, and the time component of the symmetry does not act on states and operators, but it does act on the defects. And therefore, we refer to it as a time-like global symmetry. I emphasize that in this particular example of a standard U1 gauge theory, this is really saying in a very complicated and awkward way, something which is completely straightforward. We can phrase this whole thing in a manifestly relativistic invariant way, and then these distinctions don't make a difference. In our case, however, space and time are completely different, so we need to be a little bit more careful with space and time, and this language turns out to be extremely effective and useful. So let's do it in our case. So recall that we had this funny gauge theory with the space components transform with the second derivative and the time components transform with a single time derivative. So the space-like global symmetry is R. There's an R global symmetry shifting A by a constant, arbitrarily real constant. And this acts on the operators. And I maintain this color coding that the space-like and the operators are blue. This transformation acts on the time component of the gauge field. In an ordinary gauge theory, we can transform only by this. So this is the standard action that measures the standard time-like symmetry that acts on the defect and gives us charge M. But we also have another global symmetry that acts on the defect, is this one, which is linear in X with an arbitrary integer M. So the upshot of all that is that the operators transform under an R global symmetry. And the defect, for example, this one, transforms under a U1, this U1, times Z global symmetry. Note that unlike ordinary gauge theory, here the space-like and the time-like components of the global symmetry are not even the same group. One of them is the group R, and the other is U1 times Z, which is okay because there's no Lorentz invariance that tells that they have to be the same. And not coincidentally, the time-like global symmetry is the same as the global momentum symmetry of the Lifshitz theory. I'll say more about that soon. Now let's use that to say what the theory does. So we had a Lagrangian, and our goal is to understand what the spectrum is, what the operators are, and so forth. So we do what we ordinarily do in gauge theories. We choose a temporal gauge. So it's A tau equals 0. And then we impose Gauss law, which is the second derivative of E is 0. And then we go back to the Hamiltonian and we find the spectrum. So this is the spectrum. And since the charge is of the space-like global symmetry is R valued rather than U1, we have a continuum in the spectrum. So the spectrum of this theory is a bit crazy. It's a continuum labeled by a real number Q. So we have a continuum of states even in finite volume. This is very much like a quantum mechanics with a non-compact target space. It has a continuous symmetry, continuous spectrum. But what about the defects? We talked about the operators and the states. What about the defects? This is the defect. It has a time-like symmetry, U1 times Z. And as we said, the defect carries charge M. And under the dipole symmetry, it transforms with this space that depends on X, X being the position of the space, of the particle. Now we see that the particle cannot move because of a global symmetry. This particle is at position X, and it carries two charges, an ordinary charge M and a dipole charge that depends on X. If the particle tries to move to another position, M will stay the same, but the dipole charge will not be the same. And as a result, this would violate the symmetries. And if it violates the symmetries, this is a transition that cannot take place. So Bretko already said something similar, that the charged particles carry an ordinary charge and a dipole charge, and therefore they are immobile. I felt uncomfortable about that because these are gauge charges. The gauge symmetries, the gauge charge is a charge under a gauge transformation. And gauge transformations do not lead to such restrictions of mobility. Where did this come from? Here, we face the same thing as a result of a global symmetry, not a gauge symmetry. So there was a lot of confusion, at least I had confusion, what it means for this gauge charge. Does it make sense? How do we define it in finite volume? Is it gauge invariant and so forth? So here we gave what a finite volume observer would say. A low energy finite volume observer would say the system, this gauge theory, has a global symmetry, similar to the one-form global symmetry of ordinary gauge theories. Here they are a little bit more subtle because these are a tensor symmetry. And what the global symmetry does is to restrict the possible mobility of the particle. So this is kind of satisfactory because the system has a global symmetry. So we wrote some Lagrangian and this and that, but in the end of the day, we organize everything using the symmetry. There are two kinds of symmetries. The space-like global symmetry controls the spectrum. The spectrum of the Hamiltonian is controlled by the global symmetry. And the time-like global symmetry controls the defects of the system. So that I think is satisfactory, but then we could ask again the same question we asked before. Does this continuum analysis really make sense? Because there are a lot of infinities here. There's a continuum in the spectrum. There's this funny gauge global symmetry, time-like, space-like. Does it really make sense? And the way to check whether it makes sense or not is to put it on the lattice and try and recover the same answers in a completely regularized system. So again, we have a lattice, square lattice, L sites in space, L tau sites in the time direction with periodic boundary conditions. We put a gauge theory on it, very much like in an ordinary gauge theory. In the time component, along the time-like links, these guys, we put phases, e to the I little a tau. And on the sides, we put all other phases, e to the I a. So this is well defined. The action is a cosine of what would be the field strength. It's associated with, so we take the time derivative of the thing in the sites, it's around that. Sorry, it's along this thing. And the space derivative, it's a double derivative or a Laplacian, so it covers two links like this. So it's two links times one link here. So this is the sum that we have to perform. And it's gauge invariant under these transformations. You could easily check that. And now this whole discussion of the global symmetries can be phrased on the lattice. So what are the global symmetries? We have a space-like U1 symmetry shifting A by a constant. And there's a time-like symmetry, which is U1 times ZL, not Z, but ZL, which shifts the time-like gauge fields. Now, again, the U1 factor can be interpreted as charge, and the ZL factor is the dipole charge. It's not easy to follow all the details, so don't worry about the details. The important thing is the qualitative statement that we can regularize the system on the lattice. On the lattice, everything makes sense. There's a global symmetry of the lattice action. And then all we need to do is take the continuum limit. And as we take the continuum limit, this U1 becomes U1. This U1 becomes R. And this ZL becomes Z. Again, we see something that even at the level of groups, we can say, what is the L going to infinity limit of U1? It could be U1 or it could be R, depending on how we take the limit. If we just dilate the periodicity here, we are going to get R. So the correct answer is that when we take the limit of the group, we should specify which representations we would like to keep. Which representations we would like to keep, and depending on how we do that, we're going to get different limits. So as in the matter theory, when we discussed the theory with phi or the Lifshitz theory, the lattice model has other continuum limits, leading to other tensor gauge theories with different global structures. Basically, we take the same lattice action with the same global symmetries here and here, and we take the limits such that these three groups have different limits. After we have done U1 gauge theory, let's do a Zn gauge theory. So we can do the same thing. We can do it in the continuum, but instead, let's just do it directly on the lattice, partly because of lack of time. So this is my lattice. And recall that in the U1, when the gauge group was U1, we put phases on the time-like links and phases on the sides. These were all U1 phases. What we do now is the same thing, except that the phases on the links and the phases on the sides are Zn phases. So on the time-like links, we put phases labeled by m tau. and on the sides we put phases labeled by m, and these are integers. In fact, these are integers modulo n, because if I shift it by n, it's the same u in u tau. And now we need to write an action, and there are many actions we can write. We are interested in the low energy limit. In the low energy limit, we would like the field strength to be small. That's what we always do in ZN gauge theories. And there's a simple way to do that when we write this combination of the integers, which is a field strength, and we put a Lagrange multiplier, which in this case it's an integer, enforcing the constraint that the field strength is 0. That's what we do in ordinary ZN gauge theories, and we can do the same thing in this ZN tensor gauge theories. So this is the action on the lattice, and again, everything makes sense. We run over a finite range of these integers. There's some gauge symmetry that we can easily fix. The action is quadratic, so the partition function is a finite sum. Everything makes sense, and we can discuss the global symmetries, the ground states, etc. So what are the ground states? The ground states are obtained by setting this thing to 0. So I can do that either in terms of m or in m tilde. It doesn't matter. We have to solve not differential, but difference equations on the lattice. So we have an integer m tilde on the paquets, and we need to solve two difference equations. This is 0 mod n, and this is 0 mod n. And it's straightforward to find the number of solutions. The number of solutions is n times the GCD of n and L. This is the number of solutions. So this system is completely solvable. Not only is it well defined, it's completely solvable. And we see that the number of ground states of the system is n times the GCD of n and L. Depending on the number of sites, the number of ground states is different. Now, it's always between n and n squared. It's not infinite. It's not e to the an infinite number. So it's really small and finite. And in fact, such behavior in terms of for the number of ground states, depending on the number of lattice sites, is very common in lattice models. Also in some of these, in some of models that are not as exotic as this one. But the way this formula appears here is very similar to the way it appears in other richer models, which are exotic. So one lesson that is true here, which is also true in the higher dimensional, more interesting models, is that the continuum limit, L going to infinity, is subtle. There's no limit here. This is finite, and depending on how we take the limit, we get different answers. This is quite common in lattice models. I emphasize, this is not something to write home about. This is quite common in lattice models. But this peculiarity becomes much more interesting in the higher dimensional versions of this system, where it's very uncommon. Next, we should study the defects and the operators. So the basic defect is a Wilson line that runs along the time direction. So all times say at x equals 0. So this is the defect. But unlike the problem with U1, where the gate group is U1, this defect can hop. It could be at negative time, it could be at x equals 0. And at positive times, it can be at x equals n. So this defect can hop by n units. And using the periodicity of the lattice, it actually can hop by the GCD of n and L. So the particle is not completely immobile. Already on the lattice, it can hop, but in a restricted way. As we take the continuum limit, L goes to infinity, the particle becomes completely mobile. This simple picture has counterparts in the higher dimensional cases. So as I'm approaching the end of my time, let me summarize. First of all, this is a huge field, and we focused here on the simplest example in 1 + 1 dimensions. And I talked about 3 distinct theories. One is a matter theory with a U1 dipole symmetry. This was the compact Lifshitz theory. This is what I started with. And then I studied or discussed the corresponding U1 gauge theory with a tensor gauge field. And then a ZN version of this tensor gauge theory. We analyzed them both on the lattice and in the continuum. So the lattice is under more control, and it exhibits peculiar features. And what we saw is that it can have several different continuum limits leading to different answers. However, I emphasize that the continuum analysis was done carefully actually can reproduce all these answers. So the continuum theory is subtle, but reproduces the correct answer that we get from the lattice. And all these models exhibit peculiar features. First, strange degeneracy, which is infinite or ambiguous in the continuum limit, depending on which model we discuss. There were defects with restricted mobility. Again, I use the same color code. This is space and this is time. Defects with restricted mobility, which depend on the number of lattice sites. So by how much a particle can hop, not only is it restricted, but it also depends on how many sites there are in the lattice. In these two seemingly unrelated phenomena, the degeneracy of the ground states and the restricted mobility follow from global symmetries, different kinds of global symmetries. The degeneracies reflect ordinary symmetries. That's not surprising. The degeneracy of states should reflect global symmetries, ordinary global symmetries that act on the Hilbert space and commute with the Hamiltonian and act on the operators. And the restricted mobility also follows from a symmetry, a big time-like symmetry, which acts only on the defects. So this is satisfactory because usually when we have a complicated system and we say symmetries will help us organize it, we should really focus on global symmetries rather than gauge symmetries, because the gauge symmetries are a fake, the global symmetries are real. And now we see that two different peculiarities of this system are both explained by global symmetries, but different global symmetries, space-like and time-like global symmetries. The other peculiarity of this model that I emphasized both in the introduction and when we came to it in the talk was this UVIR mixing. They are long-distance, low-energy phenomena, which are sensitive to short-distance details. Exactly how we take the continuum limit leads to different answers. We get different answers. The restricted mobility or the ground state degeneracy depend on the number of sites in the lattice. And I can say a lot more about that. Now, as I said, this model is the simplest one. The sequence of models is the simplest one in 1+1 dimensions. And it does not have the richness and the robustness of its higher dimensional counterpart. Higher dimensional versions of this story exist. Many people wrote papers on related models. And what we have done during the pandemic, the four of us, was to analyze these models from the perspective that I presented here. Namely, right, both of the lattice and the continuum to understand exactly what the space of functions in the continuum is, what is it on the lattice, how we take the limits from one to the other, what are the global symmetries, etc. But with all this understanding, there's still many interesting puzzles that I find fascinating. Since I'm out of time, I'll end by a very important comment. Happy birthday, Mike.
Any question?
Hi, Nadia.
Hi. I don't know if you can see each other.
Can he hear me?
I can barely hear you, but I can. I'll make an effort.
Okay. Do you have non-abelian versions of such models?
Oh, that's a fascinating question. This particular model, the answer is no. People try to write non-abelian versions of, so in higher dimensions, there are other models. There are more moving parts in high dimensions because there are more things you can change. And people suggested various non-abelian versions of it. The main issue with the non-abelian ones is that I've been focusing on the free models that are quadratic. So the gauge group is abelian, the action is quadratic, we know exactly what we're doing. In the non-abelian case, we have to discuss interactions, and that makes it more subtle. This is clearly something interesting to do, but I don't have much to add to this. But this is an interesting topic to address.
Yeah, okay, go ahead.
Hey, Nati, this is Vijay. Beautiful talk. Question.
Thank you, Vijay.
Is it possible to define a sensible version of these things in which the time part of the gauge transformation also has two derivatives?
Yes, and in fact, this was done in a recent paper by, let's see if I can remember all the authors. It came from Texas. Andrea Karsh, Jacques Dissler, Amir Raz, and I think there was perhaps another author. They did exactly this thing There's a version of this story in 2+1 dimensions that we studied. With this, in the time directions, it's conventional. In space, it's crazy, just like here. And they just studied the space part of it. And then you can also do that in high dimensions. So even in Euclidean time directions, you can have a high derivative terms. Once you want to give it a Lorentzian interpretation, I'm not sure what it means. So most of the condensed matter literature is actually in a Hamiltonian formulation. So if you try to write it in Lagrangian formulation, there are two derivatives in time in an obvious way, and then space could be completely messed up. And these are the systems that we looked at in a lot of detail because we thought that unitarity should be respected, and also we wanted to connect to the answers in the condensed matter literature. But the group in Texas did exactly what you just mentioned.
Thanks. You had the question?
No, I have a question. Okay, Nikita, the question. I have two questions actually. So you mentioned that the spatial Wilson line has dimension 1 in this example of tensor gauge theory. Can you hear me?
I can barely hear you all. First, let me move to the slide that you're probably talking about.
Okay, so
are you asking about this slide?
No, I think it was earlier. So when you just
So this is an ordinary gauge theory. This is a review of this notion of space-like and time-like symmetries for ordinary gauge theory.
Earlier slide.
Sorry?
Integral of A dx.
The slide before.
The slide before.
Yeah, or two. Just, yeah.
This one?
Yeah. So you could create something of dimension 0 by doing iterated integrals, right? So do two integrals.
Yeah, good. I think I can barely hear you, but let me guess what you're asking.
I'm asking about parallel transport.
I'm sorry?
I'm asking about the parallel transport for these tensor fields. Can you define it as a kind of iterated integral on plaquettes or something?
Okay, so the answer in this case is no, but there is a variant of this which does work. If you you're not in 1+1 dimensions, but in 2+1 dimensions, and you restrict the tensor to be I not equal to j, then instead of a Wilson line, then you can put it on a plaquette. See, here you cannot put it on a plaquette because the second derivative in x is along two links. And even if you go to two spatial dimensions, if you have two derivatives, di, dj, with any I and j, you still can't put it on the plaquette. But if you impose that I is not equal to j, you can put di, dj, and then what you said makes sense. And in fact, instead of doing that, we can have a Wilson strip which covers plaquettes. I emphasize that the indices I and j are symmetric indices. They're not anti-symmetric. So it's not like a B field. It's not a 2-form. These are symmetric indices. So this whole thing of Wilson strips has to be analyzed very carefully. And we've done that in the paper. We've done it both on the lattice and in the continuum. And in that case, you do indeed need to exponentiate this object. In this case, the Wilson strip needs to be exponentiated for gauge invariance. So the example in 1+1 dimensions, where the two indices are the same, is simpler. And as you go to 2+1 dimensions or even higher, the story splits between when you have a tensor, is it an arbitrary symmetric tensor, or is it a symmetric tensor with only off-diagonal terms? In the latter case, there are gauge invariant things that are operators, and they do need exponentiation to make sense of them. They have other peculiarities, but they do need exponentiation. I hope I answered your question. I answered a question. I couldn't quite hear you.
Well, you changed the question, but I think even with 1+1, you can do the double integral. So it will be a degenerate plaquette. We just double integral along the same plaquette.
Yes, that's right. So you can do that. You can write a double integral, but then it will still be something that you can express using this object.
Well, here
The question, let me again rephrase your question. Your question is, do these operators really generate everything? These and the electric field, do they generate all the space of operators? Right, that's a question you could ask.
That's a good question.
And in the paper, we wrote all possible operators that we could study. There are many more operators and many more defects in this theory. We can take, for example, two of these guys with charge R and minus R, even with real R, not only integer, and let them move in space. So you can have something like that. So there are many more objects that you can construct. Here I talked about the simplest operator and the simplest defect. If you limit yourself to operators, these basically give you the whole thing. Everything else can be constructed out of these. The geometric way of stating that has not yet been completely worked out. So I believe that there's a geometric way of stating all of these things that we said in the continuum. So what did we do? We put them on the lattice so that we're sure that what we're doing is right. We did it in the continuum so that we can write continuum expressions and we can manipulate them, and we'll learn how to manipulate them. And in some cases, we try to think more geometrically what it means in terms of transition functions, sections, parallel transport, etc. We did not push it as much as I would like. And I believe, so these systems exist, right? So there's nothing we can do about them. And it would be interesting to understand better how to think of them more geometrically. Since you asked, let me throw in something about that. Many of these systems are almost topological. These are the gapped ones, or depend on the metric. They're not Lorentz invariant. In most cases, they're not even rotationally invariant. But more globally, they depend on the choice of foliation of space-time. So foliation it's fixed. The more interesting one is, of course, foliation in space. Because let's assume that we have foliation so that different spatial sections are separated, and we can do that in a global way. But even if we did that, these systems depend on space being fully foliated and depend on the choice of foliation. In the gapped systems, which is what in ordinary systems they give us topological field theories. Here the theories are not topological, but they are almost topological. They are almost topological in the sense that they do not change under small changes in the metric, but they do change if we change the foliation. So the choice of foliation of the manifold does affect the answer, including even the number of ground states, etc. That can depend on the choice of foliation.
Yes.
But more generally, sorry?
What codimension? So foliations come
in different codimensions. So in the simplest cases, it's foliation with codimension 1. So if space is, say, two-dimensional, we have lines, foliation by lines, x and y directions locally, and how they're connected globally. In 3+1 dimensions, the foliation by surfaces, say the xy plane, the yz plane, and the xz plane, but then we can connect them in a complicated way. And there are models that even the foliation is more subtle because the leaves themselves are not manifold, but kind of crazy. So I emphasize again that what I talked about here is the absolutely simplest case in one spatial dimensions, no issue of foliation. The tensor is the simplest tensor because we are in spaces one-dimensional. The higher dimensional versions of this story are a lot richer. Both the physics and the math are much richer, but many of the subtleties and the way to organize it and to think about it is really along the lines of the talk I gave here.